Hello, dear students. Welcome to the YouTube channel and welcome to the Signal and System playlist. In this playlist, we are learning signal and system from very base. We are learning what is signal, what is system, what are the types of the signal, what are the types of systems, and a lot more. So, uh, initially, up until now, we have seen about basics of the signal, like what is a signal, what is a system. We have seen few types of the signals, like we have already seen continuous time signal, discrete time signal. We have seen periodic and non-periodic signals. We have seen analog and digital signals. We have seen even and odd signal, or in other words, we call them symmetric and asymmetric signals. Today we are going to explore about power signal and energy signals, and it is little bit different from what we have seen until now. We have uh, up until now the signals which we have seen, it was a little bit easy for us to distinguish those signals with the help of graphical representation of whatever signal given to us, but with which will not be the same case here for power or energy signals. Okay, so let's begin with the power signals first. So firstly, what is a power signal? So to put it in a simple words, power signal is uh, if the normalized power of the given signal is non-zero and finite. Okay, we call a signal a power signal if the normalized power of the non-zero normalized power of the signal is non-zero and finite, which means the power of the signal cannot be zero and it cannot be infinite. Okay, so for power signal, the power must be between 0 and infinite. It cannot be 0 and it cannot be infinite. Okay, so now you might have a question that what is the power of a signal? Okay, in general, uh, uh, power can be derived using so many different equations, right? So in general, for the calculation of the power of a signal, what do we do? So the power of given signal is given by this equation. For continuous time signal, it is given by limit t tends to infinite 1 by t integral minus t by 2 to t by 2, and uh, in uh, in the modulus we take square of the given signal and we integrate it with dt for uh, continuous time signal. So if you tear it apart in small parts, what do we do uh, for for the power? uh, Before I tell you that, let me tell you that what is power. So power is generally time average of the energy. Okay, so power is generally time average of the energy. So uh, now what do we do? The integral of xt, that signal which we are taking, we take the integral from minus t by 2 to t by 2. So that integral, what it will give us, it will give us the area under x of t. Okay, between minus t by 2 to t by 2, right? That integration will give us a area, right? You must have studied that in calculus, right? I've told you already that you will need a little bit calculus to understand this course. So by using integral, we find the area between minus t by 2 to t by 2. Then what do we do? This area we divide it by t. See, we have a 1 by t over here, if you can see. Okay, we divide it by t. So when we divide it by t, what do we get? We get the average value of xt. Okay, we get the average value of xt. And now what we will do, we will take the limit t tends to infinite. So when we will take this limit, what will happen? The average will be calculated over the entire time range. Okay, over the entire time range, from where to where? From minus infinity to infinity. So what did we do? So what did we do? We took the average of energy from minus infinity to plus infinity. Okay, Remember, initially I've told you power is the time average of energy. Okay, so uh, this is how you find the power of continuous time signal. If you want to find the power of discrete time signal, what do? We take limit again, n tends to infinite. Then we go, we take the division 1 by 2n plus 1, and we take summation n equal to minus n to plus n, and then we go, um, in modulus we take the square of my signal for dt signal. Okay, so in practice you will see most of the signals which we come across, most of the signals which we uh, deal with, will be either energy signal or power signal. Okay, um, and the periodic signals, most of the periodic signals, I'm talking about the theoretical case, not practical case. Most of the periodic signals are power signals. Okay, and there is one point that I am leaving it to discuss after we finish the energy. That is, the energy of a power signal is infinite. Okay, energy of a power signal is infinite. Why is that? Because we are taking, uh, remember what is power. Power is the time average of energy, so we are taking time average of energy. So the energy will be, if we are taking a time average of energy, that means this time average will be infinite. So energy of the power signal is infinite. Okay, now um, let's come to energy signal. Let's come to the energy signal. uh, Coming to energy signal, here you can see. So what is energy signal? So a signal is said to be an energy signal if its normalized energy is non-zero and finite. Okay, so again, if the energy of my signal is non-zero and finite, then my signal will be included in energy signal. Okay, and if you are aware of general physics, then you may know that any particular signal cannot have zero energies. So that means the normalized energy of any signal must not be infinite in order to be that signal a energy signal. Okay, so any signal that has energy, that has an energy which can be accumulated or which can be uh, calculated is energy signal. If the energy of particular signal is infinite, that means that signal is not energy signal. Okay, so how do we calculate the energy of any signal? So we use this formula for continuous time signal. What do? We take again integral from minus infinity to plus infinity, and then what do? We simply take the square of our signal. We take the square of our signal, and we integrate it with dt. Okay, similarly for discrete time signal, what do? We we take the summation which goes from minus infinity to plus infinity, and then what do? uh, we again take the mean square of my signal. Okay, uh, by mean square I mean we first take mean and then we take the square of given signal. So we are doing nothing but we are taking a mean square of the signal. Okay, so in practice, the signals, the most of the signals which you will come across, these signals will be energy signals. Most of the signals which we will come across will be energy signal. And one more important thing, in both energy and power signals, like here you can see the equation of power signal, and again here you can see the equation of energy signal. If my signal is periodic signal, then we don't have to like really take the limits. Okay, because you know already your signal is the time duration of your signal is very much fixed, so it itself applies a limit, so you don't need to apply any limits over the signal. So, and again, the energy signal, most of the non-periodic signals will fall into the category of energy signals. Except for that, the power of an energy signal is always zero. um, Always remember that any signal with the finite energy has always zero power. Okay, remember, when signal has an finite energy, that means that signal is energy signal, so that signal has zero power. And a signal with finite power has always infinite energy. Okay, a signal with finite power always have infinite energy. So that was your energy signal. Uh, Now let me move further, which is energy versus power system, power signals, sorry. So as I said a few minutes ago, that power is a time average of energy. So when we calculate the power of a signal, at that time we are basically calculating the time average of energy of that particular signal. Okay, again, one more interesting thing, that a signal cannot be both energy and power signal at the same time. Okay, either the signal is energy signal or the signal is power signal. And if the signal is not falling in either of the categories, that means the signal is neither the energy signal nor the power signal. But it cannot be energy signal and power signal at the same time. Okay, then all the signals, I've just talked about this point again a few minutes ago, that all the practical signals which we come across will fall into the category of energy signals, right? Because all the signals which we will come across will have finite energies, which means the duration of those signals will be finite. And if the duration of a signal is finite, that means it cannot be a power signal. Okay, in order to signal for a signal to be a power signal, it must have infinite duration. Okay, and any practical signal which we will take, it will not travel for infinite time duration. Okay, so any signal that have that runs for finite duration of time, that falls into an category of that can never fall into the category of power signal. But it is still, you have to find out if that signal is energy signal or not. It can be energy signal or it cannot be energy signals. Okay, but in order to be a power signal, a signal must necessarily have infinite duration. Okay, it must run for an infinite duration of time. Okay, then again, we have some interesting facts and interesting stuff, that if you observe a signal, and if that signal, it is having a periodic that signal is a periodic signal. Okay, we have discussed what is a periodic signals in two videos ago. If you haven't seen the video, if you want to know what is a periodic signal, you can see that video. The link will be flashing in the I button on the top right hand corner of this video. So if you want to know that, please check out that video. But if you're already aware of that, so that signal, let's take a signal which is a periodic signal, and it is running for infinite duration of time. Okay, if a signal is a periodic signal and it is running for the infinite duration of time, then that signal can be a power signal. There is a high probability that that signal will be power signal. Okay, so in such case, when we see that okay, this signal is running for infinite duration of time, and it is a periodic signal, then you will what we will do, you will first calculate its power. Okay, so there is a more probability that signal will be power signal. But again, I've already told you that in practical scenarios, not a signal never runs for infinite duration of time. That means practically no signal can be a power signal. Okay, but mathematically it can be. Okay, then again, taking the other scenario, other case, that if you see a signal is a periodic again. Okay, you are taking periodic signal again, but it has a finite duration of time. It is running for the finite duration of time. Okay, for finite cycle it is running, then that signal can be energy signal. So in such case, you what you will do, you will calculate energy directly. Okay, in any of the cases, if you see that my signal is running for a finite duration of time, you will calculate energy directly. Okay, it doesn't matter if it is periodic or non-periodic. So third case says the same, that if my signal is non-periodic signal, uh, then also this signal can be energy signal. So you must calculate its energy directly. Okay, but again, as I've already mentioned, that if it can be, my signal can be power signal, my signal can be energy signal, but it is not mandatory that every signal will fall in the category of power and either power or energy signal. Okay, in previous cases, previous classifications of signals, we have seen that signal is either every signal for our what do you call it, for continuous time, a signal can be either continuous time signal or discrete time signal. Okay, but the signal must be either continuous or discrete. But if you are saying that my signal is neither continuous nor discrete, that is not possible. Okay, same, your signal is either analog or digital. Again, same ways for either your signal is periodic or non-periodic. There is no third category, or there is no exception that my signal is neither periodic or not nor non-periodic signal. That never happens. Either your signal is periodic or it is non-periodic. There is no third category. Okay, same ways we have seen in even in odd functions, even in odd signals, we have seen that every signal can be represented with two parts. Every signal can be represented using two parts, even part and odd part. So a signal can has even part and odd part, or a signal can has either one of them. It can has even and there is no present odd part. It can has odd part, no present even part. Okay, but for energy and power signal, that there exists the third possibility, that either your signal can be energy signal, or your signal can be power signal, or your signal can be neither of them. Okay, there is a strong probability that if you are dealing with few rare signals, then it can be neither energy signal nor a power signal. Okay, there are some cases. Let me walk you through such cases. Like one of the cases that I have mentioned in the presentation here, that e raised to minus 80, if you take calculate the energy and power of that signal, you will find out that e raised to minus 80 has a infinite energy. Okay, so that signal is neither energy signal nor a power signal for uh, for any real value of a. Okay, if you are taking any real value of a, then it is neither a energy signal or power signal. But if you take a an imaginary number, okay, you must have studied complex numbers in calculus, and in that we can take complex number a plus ib. Okay, we take a plus ib. If you are in different fields, we represent uh, the complex the imaginary part of complex number with I, multiple of I, like we multiply it with I. Some cases we do it with I, some cases we do it with j. Okay, in mathematics we use I, in electrical engineering sometimes we use j. So basically a complex number is a form of y is equals to a plus ib. Okay, so if you are taking imaginary part, then the signal can be power signal with power of 1. Okay, now let me mention some other cases. So another case is a ramp signal. Okay, if you are taking a ramp signal, then if you calculate again its power and its energy, you will find out that the ramp signal is not neither energy signal nor a power signal, right? Because what is a ramp signal? Signal is a signal which is starting from origin, and it is passing through your 1 1 2 2 3 3 4 4 till infinity. Okay, and when you will calculate the energy and power of that signal, you will find out that okay, this signal is going towards infinity. Okay, it can be power signal, but then you will find out that oh, it is not a power signal. Then again you will calculate its energy, and then you will find out oh, it's having infinite energy, so it is neither energy signal nor a power signal. Okay, so a ramp function is another example. Then again, one very interesting scenario or one very interesting case that uh, builds up, that if you are taking x of t is equals to t, okay, x of t is equals to t, and then you calculate the power and energy of that signal, because mathematically you can write x of t is equals to t, but uh, how do you graphically represent it? So energy and power of that signal depends on the graphical representation of that signal. Okay, so again, the energy and power for x of t is equals to t will be uh, infinite. For energy will be infinite, and power is also will be infinite. That means and definition says that power, if my signal is energy signal, if the energy of that signal is finite, but we are having infinite energy, which means this is not energy, this signal is not energy signal. And the definition of power signal says that the power of any signal must be between 0 and 1, sorry, between 0 and infinity. But we are here, here we are having the power of infinity, so it is not power signal either. So x of t will not fall in either of the categories of energy signal or power signal. Okay, and before we conclude the energy and power signal, I want to talk about one practical thing, that in practicality you will not find any power signals, because a signal can never have a signal can never run all the time, like signal cannot have infinite time duration. So all the signals that you deal with in practical scenarios will be energy signals, and practically it is impossible to generate a true power signal, okay, in practice, because again, any signal cannot run for infinite duration of time and cannot have infinite energy, right? So uh, that was what energy and power signals were all about. Now we will be moving forward, we will be discussing few other types of signals. Let's talk about deterministic and random signals. So what is a deterministic signal? So a deterministic signal is a signal whose physical description is known completely. Okay, and basically it is very simple. A signal to be a deterministic signal, its physical description must be known. Okay, it must be presented either in mathematical way, in mathematical form, or a graphical form. Any signal that can be represented by any mathematical equation, or it can be represented by graphically, that signal is deterministic signal. Okay, for example, you say x of t is equals to cos omega t, or say x of t is equals to sine omega t, or you say e raised to minus alpha t, e raised to bt. You take any signal that can be represented by mathematical formula, that signal is deterministic signal. Okay, and the signal, the random signals, and again let me tell you that if you are whatever field you are from, whatever you are learning, most of the times you will be dealing with deterministic signals, because if you are from electrical engineering background, you'll be dealing with the power systems, power electronics, or if you are dealing with microprocessor controllers. If you are from EC background, you are dealing with controllers, processors. You will be dealing most of the times with these signals, deterministic signals only. uh, if you are working in few few domains, like if you are working in image processing, in that sometimes what you have to do, you have to generate noise in your image, you have to insert some noise in your image. So for noise generation purposes, for image processing, computer vision, you will be having random signals. Okay, so what is a random signal? Random signal is a signal whose value cannot be predicted precisely, but known only in terms of probabilistic description. Okay, what are the probabilistic descriptions? you can say mean values or mean square or RMS values, right? All those values are uh, probabilistic descriptions of any signal or any function in general. So such signal is called random signal. If you want to explain them in layman's term, then you can say that any signal that does not have any mathematical formula, a signal which cannot be represented by any mathematical formula, is a random signal. Okay. And again, what are the examples of a random signal? So I've said already that noise generation. If you are if you want to generate noise in as I've said, image processing, or if you want to generate noise in electrical components, right? Sometimes in power electronics you need to generate noise in electronic components, right? If you want to generate noise in transmission channels in power systems or cables, so for that noise generation purposes, random signals are used. Okay. So that was deterministic and random signal. Let me show you the graphical representation of the same, so we can uh, graphically show the deterministic and random signals like that in the image that is shown here. The A image is you can see it is a cosine. Okay, it is a cosine or cos signal, and we can represent it cos signal with its mathematical formula, which means it is a deterministic signal. Again, here in image B, you can see the second is what is it? It is rectangular pulse. Okay, and what value it is having? It is having one value, which means it is unit rectangular pulse. Okay, so this unit rectangular pulse is also can be represented with the help of mathematical formula, right? We can mathematically give a formula of that, which means this signal is also a deterministic signal. But look at this signal C, right? Can you represent this signal, the C signal, with the help of any mathematical formula? Probably you won't be able to represent this signal with the help of any mathematical formula, right? Even if you want to, you will need too many polynomials and too many degrees of them, because this is very, and the whole formula will become too complicated. Too much complexions will be there, right? So this signal which not will be able to we will not be able to represent it with you with the help of any mathematical formula, which means this signal, the signal C, falls into the category of random signals. It is a random signal. Okay, so up until now we have seen what type of signals we have seen. We have seen continuous time signal, we have discrete time signals, we have seen analog signals, we have seen digital signals, we have seen periodic signals, we have seen non-periodic signals, we have seen even signals, we have seen odd signals, we have seen energy signals, and we have seen power signals, we have seen deterministic signals, and we have seen random signals. Okay, in this random signals, the random signals which I'm talking about, these random signals are also known as stochastic signals. Okay, so in exam, if you are asked what is a stochastic signal, it is nothing but a random signal, which means a signal which cannot be represented with the help of any mathematical formula. Okay, so it is also sometimes called stochastic signal. So we have seen this all the signals till now. Also, by the way, union node are also called symmetric and non-symmetric functions, or symmetric and non-symmetric signals sometimes. So that was pretty much of classification of signal from my part. Now in the upcoming lectures we will be seeing some very useful signals, some signals in particular which will be very useful to us in calculation part. So we will be visiting them. Up until now in this lecture, or even any other lectures from this playlist which you have accessed, if you have any doubts, you can mention it in the comment section below. I will try my best to give it a reply as soon as I can, and I'll be seeing you in the next lecture, in which we will be discussing some important functions. So till then, take care everybody, and yeah, that's it. uh, Goodbye, take care.